light and ground base aren't always available. And then there's a geometry problem where satellite look down, not always vertically, but tend to look down in a vertical manner, whereas the ground-based methods have a variety of viewing geometries. And so finding metrics for direct comparison is not always easy. And then finally, there's a timing problem where satellites provide snapshots of one image of a plume at a given time, whereas on the ground, we tend to see time series of a slice of a plume and not the whole plume. So deriving time series metrics from satellite image is not always trivial, although there have been great advances in the last few years to provide this. And so this is another motivation to improve retrieval methods and provide more metrics for comparison, maybe more direct metrics for comparison. And so when looking at the monitoring tools that exist now, there are great strides that are being made in SO2 cameras, where we combine spatial and spectral information. So this is a two-dimensional multispectral imager with frame rates that are coming down below 1 Hertz now, and usually coupled with a high-resolution spectrometer in a subset of the frame to do some calibration. So those provide quantitative maps of SO2 concentrations coming from plumes. In terms of the equivalent in the infrared methods, they tend to be used in a very different way and typically more sporadically. Broadband infrared cameras are used for thermal monitoring, usually of effusive features, lava flows, lava domes, and not so often for looking at volcanic plumes. And the ground-based infrared spectrometer, which is the topic of this talk, the OpenPath FTIR, tend to be used when looking at hot plumes, with a high temperature source. That's the standard operations. So either a lava flow or a lava fountain in the background, or an artificial source. And then they can target a wide range of target species and especially gas ratios to look at the composition of volcanic gases. But those require usually very specific viewing geometries, and the instruments can be expensive and delicate. And so they're usually not deployed as routine monitoring tools in terms of in peacetime outside of those specific conditions. So the goal of our approach was to try and use the OpenPath FTIR to observe the self-emission of radiation from a drifting plume. So looking upward with a sky background, a cold sky background. So the advantages would be to target a wider array of plume components when compared to the UV methods that are usually used for this in this configuration. So not only the SO2 gas, but also ash and aerosol particles. And then this would open the door to nighttime monitoring with the OpenPath FTIR and nighttime monitoring of gas species. And then potential integration with multispectral imager, and in general, just expand the range of applications for these often expensive instruments. So the first approach was actually a project I did in 2015 during my first postdoc, was to try and get a comprehensive solution with a hyperspectral imager. And so this is an instrument that works in much the same way that an OpenPath FTIR would work. So a Fourier transform infrared spectrometers, but it projects onto a two-dimensional array. And so the spectral range is typically between 7 and 14 microns. And it produces for each pixel, and this is the great advantage, a full spectrum. But then there are significant drawbacks. So the first one being that this instrument is extremely expensive and delicate and very difficult to deploy. But beyond that, there's also some complex viewing geometries within any given scene and a large variability between scenes in a time series that make producing a consistent data processing pipeline quite tricky. And then of course, the large amounts of data that are produced by those instruments and the associated time that can be necessary to process them, especially when using full-scale radiative transfer iterative models, can become prohibitive. And so one thing that we looked at was the use of qualitative indicators to get an idea of where the gas or ash is within a scene, and also a relative measure of the intensity of the emissions. And so I'll detail 3 of them here. The first approach that we used was a curve fitting approach, where we essentially normalized the spectrum that we measured. So in this top panel here, you see a normalized spectrum, and then compare it to what we expect an SO2 emission signal to look like, and then just give it a correlation factor, Pearson coefficient. And so we produce maps, and this is very fast computing and essentially allows us to flag where the SO2 or the ash may be in a pixel. Then when looking at time series, so this is about an hour worth of data at Stromboli, and I've identified 3 different events here, 3 different bursts from the Stromboli craters. You can see that essentially it also allows us to identify individual events, and so will help us redirect computational resources towards only the worthy kind of events, if you will. Another type of qualitative indicators that also allows fast processing and principal component analysis, or PCA. And so this is a slightly different approach. So we take a subset of pixels, in this case, all the pixel within a scene that have a sky background. So we just remove the edifice. And then we calculate the eigenvalues and eigenvectors for this subset of pixels. And essentially, we usually end up with 3 to 5 principal components which have statistical significance. And within those, we can identify the signal that is flagging where SO2 and ash might be in a scene. So again, a great way to identify SO2 and ash bearing pixels. The third time of qualitative indicators that we investigated are brightness temperature difference indices. And the reason we did that is because it's a very common way to look at multispectral data, especially in satellite instruments, but also in ground-based instruments. And so the principle here is to define an on-peak band and an off-peak band, and to essentially subtract the brightest temperature measured in one by from the other. And so we've tested 4 different indices by varying where the off-peak band might be in our spectrum. And then we can generate some, again, quick indicators. And those also provide a relative measure of the strength of the signal. And so this might be a measure of the concentration of the target species, in this case, SO2. And so what we can see is for those 3 events that I looked at before, the A, B, and C event, you can see these indices where we vary the off-peak frequency, and they can produce very widely different results. So some of them, for some events, the results look very similar, but from some other events, they might look very different. Particularly this C event, which is an ash burst, looks very different depending on which indices are chosen. And so the thresholding is also problematic because the noise level can vary between scenes over the course of a time series. And so finding a good threshold for those brightness temperature difference indicators can be difficult. This is apparent in the time series where you can see that they produce very different looking time series, and flagging where the events occur in the index number 3, for example, might be very difficult. Whereas the qualitative indicators such as curve fitting or the principal component analysis do a much better job of being able to identify the events of interest. And so the last thing that we looked at was the effect of the spectral resolution And this is a way of looking at what would happen with a bandpass filter instrument. So the indicators I showed you before were constructed with bands of 10 wave number resolution, but that's very unrealistic if considering a multispectral imager. Most commercial manufacturers have much higher bandpass filter resolution. So when increasing this resolution, so it's essentially widening the band of the on-peak and off-peak frequencies, you can see that the noise level increases really quickly. And when you get to a much more realistic 200 wave number filter, you get results that are that quickly become really difficult to interpret. And in fact, if you look at the image here with this wave number, the signal is almost inverted, where the high values are not the SO2 pixels, but they're in fact in the sky behind. So in conclusion, we've seen that those qualitative indicators can be good for pixel identification and pixel flagging, essentially, to identify the SO2 and ash-bearing pixels, and then get a relative measure of the signal strength, and then direct computational resources for more intense processing, such as the one that I will get into later right now. One other thing that we noticed is we had a UV camera with us pointing in the same direction. And although the UV camera is a lot more sensitive to weather conditions, and we had actually a hard time gathering data sets to compare because the weather conditions were not ideal. So that's a great strength of the infrared method. But the concentrations that we retrieved with this camera were significantly higher than those we retrieved with the SO2 camera. And so this is also a way that we can look at what exactly we're measuring with each of the method and how to interpret those quantitative measures. This has been also noted by some colleagues, Nathalie Huret and others, who have taken the same instrument at Etna and looked at the part, and they've implemented the radiative transfer model, a full-scale iterative radiative transfer model. And they've also seen some disparate discrepancies between the UV camera and the infrared methods that I think are worth exploring. And then they exposed the biggest drawback, I think, of this method, which is the large computational time, in their case, 1 week for an entire scene. And so the need for faster methods is quite clear. And so here at Oxford, what we've tried to do is to simplify the approach, to go back to a single pixel open path FTIR and to try and implement a fast retrieval to get quantitative metrics on those instruments. And so our strategy was to have a viewing geometry with elevation angles of 25 to 30 degrees in general. And then we looked at the plume, placing this field of view at various distances from the vent to try and see if what kind of effect we get. And then for each set of measurements, we took a clear sky spectrum to try and get an idea of what the radiance at the sensor would be outside of a plume. And so what we've realized is that it's very important to keep this clear sky at the same elevation angle, but pointing it in the different directions. And so here for the forward model that we've developed, we use a 3-layer approach, where essentially if we look at the radiance at the sensor measured by the observer, it's a sum of 3 components. The first one being the emission of the gases between the observer and the plume. And the second one is the emission of the plume components themselves, which is then has to pass through this proximal layer. And then the third one being the emission of all the top of the atmosphere, which passes through the plume and the proximal layer. So if you forgive me this kind of rather messy slide, what we have here is, if we look at the clear sky measurements, we have those three components here, and we can model this with a reference forward model, which is a full radiative transfer model developed here at Oxford. We use local soundings to replicate those clear sky measurements. And then with the fast forward model, we can replicate this using the references that we've produced and only changing the plume components, essentially. And so what we're trying to replicate is the radiance difference between the measurements we take in the plume and the measurement of a clear sky. And to do that, we essentially compute the transmissivity of the plume from reference quantities. So we use the RFM, the reference forward model, to simulate the transmission of each of those species within the plume layer for reference quantities. And then we use the fast forward model to scale those. And so we use these are examples of the reference extinction profiles that we generate. And so the four big things that we vary, or parameters that we vary within a retrieval, is the scaling factor for the water vapor within the plume, and then the SO2 concentration, the aerosol number concentration, and then the ash number concentration. And so if I can just draw your attention here to the bottom panels. So what I've shown here, instead of extinction, absolute extinction, is just a normalized extinction to show you the variations in the shape of the profile over the wavelengths that we consider with regard to the size of the aerosol parameters. So the sizes here are log normal distribution, and this effective diameter is just the center of that log normal distribution. And as you can see, for the aerosol, the sulfate aerosols, there's a significant variation in shape, whereas for ash, mostly the shape remains the same, except when considering very low size ranges, effective diameters. And so I'll just show you some results of the radiance difference that we fitted. So in the top panel, this is the measured spectrum in blue and the model spectrum and this is against the radiance difference between measured spectrum and the clear sky spectrum. And in the bottom panel is the misfit. And you'll see there's those SO2 features. So you'll see over time, there's pulses of SO2 coming in and out. And then there's also pulses of ash coming in and out, which have a much broader effect. They essentially act like a black body emitter. And then if there's one more thing, I think it will show up in a few seconds here, is on the shoulder next to the SO2 feature, you'll see some variations that are actually due to the sulfate aerosols and the amount of sulfate aerosols. So perhaps, I guess it's not showing. Yes, in this area here, the shoulder of the SO2 absorption feature or the emission feature, there are some wavering in and out, and those are due to sulfate aerosols. So the retrieved quantities here are the SO2 slam column density, and then the particle density for ash and aerosols, and an effective diameter for ash and aerosols. There's also a plume temperature difference, so we allow the plume to be warmer than the surrounding atmosphere. But we found that best results are obtained when this is not a free parameter, but a set parameter. And then there's a water vapor scaling as well. So if I show the time series results here, we haven't fully investigated what this means, but the top panel shows the SO2 slant column density. And then the second one is the green line, the solid green line is the aerosol optical depths due to sulfate aerosols, while the dashed line is the variations in the effective diameter of those aerosols. And then a similar approach for the solid and the dashed line in ash here in gray. And then in blue is the scaling of water vapor within the plume. And then you can ignore the delta T of the plume because it's set at 5 degrees, but then the cost here associated is in the bottom plot. And so what you can see is that there are some events where the misfit is much more pronounced, and those are essentially the ash emission events. And so we're working on trying to fix that. And I think there are some issues with the size parameters and the size distributions that we're considering. But then there's some good things that we're seeing in the in retrieving the effective radius of the sulfate aerosols, and we are able to independently retrieve sulfate and SO2. And so I think that's a good way to move forward. And when not retrieving the sulfate aerosols, the SO2 time series looks very different. And so it's very important, I think, to be able to retrieve both of those at the same time. And a similar thing can be said for the ash. But there's also a potential codependence of particle concentration and particle size when it comes to the ash, where you have this seesaw pattern. And we think that's probably because the ash spectral shape that we consider does not change significantly with size, which means that increasing the size or increasing the burden of ash in our retrieval has essentially the same effect. And so this creates these things where the model kind of tries to increase one or the other and gets the same result. And so we're working on that. Maybe we're not considering appropriate size distributions, or maybe not appropriate spectral parameters, so the complex refractive indices for the ash. However, if we are considering the right one, then this might be something we have to live with. It might be very difficult to retrieve both size and ash burden at the same time. So one thing that we also had was an independent validation. So while we were doing those measurements, we also had in-plume sampling with a drone. We were only able to retrieve one small sample. It was contaminated by shards of propeller blades, and we definitely had a size bias where the fine fraction was trapped in the sample bag. So the size distribution that we retrieved had an effective diameters of 180 microns and a pretty wide array of sizes. So rather on the large size in terms of particle sizes, but again, we definitely lost the finds in the bag. So we'll be working on the next, correcting this for the next field work. So in conclusion, I think we've shown that we have a fast quantitative retrieval for this type of measurements to retrieve SO2, sulfate aerosols, and ash quantities simultaneously. And this method can produce something that's more directly comparable to some satellite retrievals, namely EASI and AIRS, the infrared spectrometers. And all of this is done with a fast processing time. So the reference generation takes a couple of hours, but then after that, the model can be implemented in near real time. And this, I think, has implications for future of where we take ground-based monitoring tools such as these. And one thing that we can do is, I think, significantly expand the range of applications for those instruments that already exist and that are at volcano observatories. And a way to investigate the variations in the emissions of ash and the concurrent emissions of ash and SO2 and their high frequency variations in time. And then this would enable nighttime monitoring of gas emissions as well from the ground. And then something that is a sort of maybe personal project, but I think we can work towards the development of multispectral imager. So something similar to the UV bandpass, the UV camera, the SO2 cameras, with the integration of an open path FTIR as a calibration method, and perhaps expanding this to multispectral system. And so in terms of short-term future work, there's clearly a need to investigate the existing data set and then create near real-time scripts to distribute to our observatory partner so that this can be developed and deployed in the ground more quickly. And then revisit the hyperspectral data with this method as well, now that we've flagged all the pixel and that we have a way to quickly process the data. And think about the integration with other instruments. In terms of long-term future work, I think I would really like to deploy these methods at other eruption sites other than Stromboli. So Kilauea, Iceland, and Etna are three great targets for future work if and when international travel becomes a little bit easier. So I'll just leave you with our plan for the future work of Stromboli, but what we're trying to do is collect more data, of course, but then also cross-validate these with co-located ground-based equipment such as broadband infrared camera or SO2 cameras, and then increase our efforts to do the independent validations with in-plume sampling of ash, but also ash, gas, and other parameters. Thank you.
Thank you, Jean-Francois. That was great. It's really cool to see the development of the system. We do have time for questions and discussion. And so please feel free to use the raise a hand function. That's if you click on the participants, it should be an option under that. Or you can type a question in the chat. And as people kind of gather their thoughts a bit, I was kind of wondering about, in terms of implementation and actual kind of practical use, if you arrive, do you pretty much stick to a fixed point, or can you actually raster your point to try to look at, particularly the edge of a plume versus the central point of the plume, if you're trying to get at, relative concentration of ash and aerosols in a plume that might be in training, the surrounding it?
So, yeah, rastering is possible. We've done actually some sets of measurements with a scanning, kind of much like a scanning DOAS might do. So scanning across the plume. The issue with that is that the main intensity fitting parameter for the retrieval is the viewing angle, and it's extremely sensitive to that. And so the reference, all these reference computing intensive iterative method has to be done for each elevation angle, essentially. And so if you modify that, then you suddenly have to create a lot more reference information, but it is possible. And once we've developed and produced enough of those reference data sets, I think we can probably get to a method that will work this way, yes.
In terms of the computation, is it, I mean, I guess it's like it's a great target for parallelization. I guess, is that the usual strategy, is to, if you have different standards, just basically ship them off to different GPU or different cores? Is that?
So yeah, I'm just doing this on my laptop so far, so I haven't looked into parallelization. But I think what's happening is I can generate a bunch of reference data sets, and we can create lookup tables so that once a particular viewing situation or viewing geometry has been created, then we can quickly go back to it without the need for creating new data sets. So as I'm going through this is becoming faster and faster, essentially.
Other questions out there? I guess I had another question. Oh, Ben, do you have a question?
Yes. Hi, Jean-Francois. Thanks for a nice talk. I guess two questions. One, on the data processing side, how large are the individual file sizes? Like for one spectrum, 1 pixel, if you were rastering, how big is that file?
So I assume you're talking about the hyperspectral camera?
Sure, or even the open path FTIR, like a single data point. How big is it? I'm wondering if it's the kind of thing that could be the data could be sent from an observatory to some other place for the data processing to a supercomputer site.
Yeah, no, a signal spectrum is not very heavy. It's a matter of the ones we have are 150 kilobytes, I think, something like that. But I think it can be even it can be made smaller if you bypass the proprietary formats of some of those and go straight to ASCII. I think that's probably possible as well.
Okay, cool. And then the other one was about what the data you showed today were very interesting, but they were also all from, for the most part, pretty small eruptions, pretty small plumes. What's the saturation, or how, phrased another way, how big of a plume or an eruption could you look at before your signal is swamped, before you don't get any retrieval at all?
Yeah, that's a good question. So here it's clear that we can still see the SO2, but I suspect that it would not take a lot of ash to completely obscure the path, in which case then we're not looking through the entire plume anymore. And we're only seeing the surface essentially of it. Placing some boundaries, some quantitative boundaries on that wouldn't speculate, because I think it's also highly dependent on what kind of particle sizes that ash actually is. If it's a gas plume, I think the method is pretty robust, and I suspect it would fail later than say a DOAS retrieval might, in that regard. So it might remain linear for a longer period, because I know that those are some of the issues with the DOAS retrievals, is that especially when there's a lot of aerosols, they can quantification might become difficult, and I think maybe infrared could provide an alternative, or something at least complementary.
Great, thanks.
Other questions? Feel free to use the raise a hand, or just get my attention anyway. And we're a small enough group that you can definitely unmute yourself like Ben did and ask a question. I guess I had a question a bit about, you alluded to satellite and these ground-based measurements and kind of making comparisons. And I've wondered, if you've had a chance to try any of this out, or just kind of a future plan.
Yeah, that's kind of a future plan. So the Stromboli is probably not the right target, especially when thinking about those infrared instruments like IEASI or AIRS. Their pixel size is really large, and so they typically they wouldn't be able to pick up events from Stromboli. It's certainly not of magnitude that we're looking at here. So what we would really like to do is go back to Etna and look at some of those events. So at this point, but because the method is very similar to the retrieval that is developed here in Oxford for IEASI, and so I think there's a very interesting comparison to be had here.
Absolutely. Yeah, to me, it's particularly exciting to think about thinking about how the grain size might vary in response to even hydrous processes or entrainment and whatnot. So kind of interesting to think about how you might be able to get at some of the small scale detail here that you would miss in more remote observations. Right.
Well, and so I think that we might get some better results if we were looking further downwind as well, because these are pretty coarse grain sizes at that scale, and I think that's not really helping the method in terms of retrieving the particle size, where the shape of the emission is a lot more dependent on the particle size when you're considering particle size of an order of a micron or less. So further downwind, that becomes a lot more important. Whereas here, I think it's acting very much like a black body, and we can't really retrieve the size and the burden at the same time.
Right. Yeah, I suppose the challenge is just getting the placement correct before the event. And yeah. Well, other questions from the general audience? If not, I suspect there are lots of more specialized questions. If Jean-Francois has a few minutes, we can sort of adjourn and have that moment where everyone asks questions at the podium, so to speak. But thank you once again, Jean-Francois. This was really great to hear about the development. I think we're all looking forward to the future development and papers coming from this technique.
Yep, stay tuned. It's coming out soon, I think.
Absolutely, that's great.